Okay, so welcome to the final video on this AGU poster on infrequent earthquakes in Malawi and how we're addressing them in seismic hazard. So in this video, I'm going to walk you through some of the results we have from a probabilistic seismic hazard assessment that we performed for Malawi that's considered three stochastic event catalogues that I discussed in the previous video. So the fault source catalogue, which is based on the data that is compiled in the South Malawi seismogenic source database, a background catalogue that considers aerial sources that have previously been defined for East Africa, and combined catalogue, which essentially is just a combination of the fault source and background catalogue. So I'm going to be first off talking about some site-specific PSHA, which is considering the city of Zomba, which you can see on the map here in the top right. It's situated on the edge of a rift, and this is a city with a population of around about 100,000 people. So the headline value in terms of the peak ground acceleration for 10% probability of exceedance in 50 years is 0.18 G. So we're anticipating quite a higher hazard than has previously been defined for Zomba based on a PSHA that just considers the instrumental record alone. But what's quite interesting is when you look at the hazard curves for Zomba here in A at PGA and B at a spectral acceleration of 3 seconds. If you think about the combined hazard curve and how much it reflects the fault sources, the blue line, and the background seismicity, the red line, we can see that fault sources become increasingly important to the combined hazard curve at low probabilities of exceedance and also at longer vibration periods. So the 3-second hazard curve is essentially just a function of the hazard from the fault sources event catalogue. Looking at disaggregation plots for Zomba gives us a similar impression. So we can see here that for 10% probability of exceedance in 50 years, the hazard tends to be dominated by magnitude 6 to 7 earthquakes, which could be a reflection of fault sources or background seismicity, or occurring quite close to Zomba. Whereas for a 2% probability of exceedance in 50 years and a longer vibration period, then the hazard is mainly a function of kind of magnitude 7 to magnitude 8 earthquakes, which can only really be occurring from our fault sources. Then looking a bit more regional scale and looking at the seismic hazard maps that we've developed using this approach, so considering that background seismicity, considering the fault sources, and considering a combination of the two, we can see how fault sources are very important, and our approach is really suggesting the active faults that we can identify in southern Malawi are very important in terms of the spatial distribution of its seismic hazard. And finally, what we're showing here is a comparison of our results in B to those that are currently on the Global Earthquake Model Global Seismic Hazard Map. So this is for 10% probability of exceedance in 50 years. And whereas this previous analysis, which again is just considering the instrumental record, can only really show a fairly uniform hazard across southern Malawi. By including this active fault information, we're showing a much more spatially variable hazard, and also overall a hazard that's increased. So overall, I think what our work is showing is that by including geologic and geodetic data in East Africa, even though we don't have any on-fault slip rate measurements, we can use some kind of geological theory on how regional strain might be distributed. We can use that information in a meaningful way in seismic hazard. So I hope you enjoyed these presentations, and please do feel free to contact me if you have any questions.